In this lesson, we're looking at solving equations over complex numbers, which essentially is looking at solving equations including complex factors, which means we'll probably start by looking at factorizing. So we'll start with something simple, and it should be something that we already know. We know dots already. So we know difference of perfect squares. When we have a squared take b squared, it's equal to a plus b and a subtract b. And so when that expands out, we have our a squared plus ab take ab, and then take b squared, which is how that works. When we have a sum of squares, or a sum of perfect squares, then, and we're looking at a squared plus b squared, generally we say there is no real factorization. Now that's because if we look at this, we've got a squared plus b squared, and we go to solve it, let it equal to 0. When we're looking to solve a in terms of b, we get an issue because when we square root both sides, we get square root of a negative. And so this would become a is equal to plus or minus. Don't forget our plus or minus when we square root of negative 1 and square root of b squared. So we end up with a is equal to plus or minus bi. And really that's saying that a plus or minus bi is equal to 0, which means that we get our two factors. And essentially what we're trying to look at here is that a squared plus b squared can be factorized if we're looking at complex numbers, and it will be a plus bi and a subtract bi. Now this is something now that we should be able to remember. Okay, so a squared plus b squared is a plus bi, a minus bi. So we'll start by looking at a simple example with that. Okay, so in this scenario we're just looking at two simple sum of squares. We've got z squared plus 4 squared, and so that will factorize to be z plus 4i and z subtract 4i using that sum of squares factorization we talked about previously. When we look at part B, we notice that there's a common factor of 2, so we always still think about common factors first. We can say that's 2 multiplied by z squared plus 3, and that would be the same as saying z squared plus square root of 3 squared. And so that factorizes as 2z plus root 3i and z subtract root 3i. So this is pretty important, that jump here when we went to factorize, treating that 3 as a square factor of root 3 squared, so we can then factorize as a sum of squares. So this will have to be a known strategy for factorization questions, particularly when we're factorizing over C. When we take the next step and we're factorizing in this standard quadratic form, then the only approach that we can take is completing the square. So when we're looking at more complex scenarios, we're going to have to be a little bit tricky. Now, if we can complete the square, which shouldn't be too difficult, the only difference is that at the end of it, we're going to end up with a sum of squares. So if the task is factorizing, remember factorizing and solving are two very different things. So there can be different approaches. If the task is factorizing, we're going to have to take completing the square as a process. So let's look at a couple of examples involving that. So in this first example, we've got z squared plus z plus 3. So when we go to complete the square here, we're going to split up that z squared and z from 3. When we complete the square, we're adding on half of the coefficient of this linear term. So we're looking at z squared plus z plus 1/2, so half of 1 all squared. And at the same time, we'll subtract that because we've added 1/2 squared in, so we'll subtract that 1/4. So that leaves us with z plus 1/2 all squared. And we have 3 subtract 1/4 is the same as 12 on 4. So 12 on 4 take 1 on 4 leaves us with 11 on 4. Now the goal is that we can see this as a sum of squares. So we can look at this as z plus 1/2 all squared. There's our first square. And square root of 11 on 2 all squared. So square root top and bottom. And that means now when we factorize, we've got our z plus 1/2 and plus root 11 on 2. And we've got z plus 1/2 and then subtract square root of 11 on 2. And there we have it. There's our factorized form. When we look at part B, we take the same approach, but in this scenario, it's a little bit more complex because we've got a coefficient of 2. So now we're looking at 2z squared, take z plus 1. And so when we take that coefficient of 2 out in front, z squared, take 1/2 z plus 1. So if we take the common factor of 2 out, we need to take it out of each here. Now we're going to complete the square. Z squared, take 1/2 z plus half of this squared, which means we're looking at -1 on 4 squared. We have plus 1. Now, because we've added on 1 and 16 multiplied by 2, we have to subtract that out. So we're subtracting 2 on 16, or 1 on 8. So we have 2z subtract 1 on 4 squared, and 1 subtract 1/8 is 7/8. Now the only issue is this coefficient of 2, so we need to take that out of the whole thing. And so that becomes 2, and we've got z, take 1 on 4 all squared, and 7 on 16. And if we want to write this as a sum of squares, it's 2, z take 1 on 4 squared, and square root of 7 on 4 squared. Now we can use our factorization. So we've got 2, we've got z subtract 1 on 4 plus root 7 on 4. And we have z subtract 1 on 4 take root 7 on 4i. Now I just realized in this first example I left out the I, so please don't do that. That sum of squares, that second term must be imaginary. Alright, now part C is quite complex. We've got 2z squared, take away 2 lots of 3, take I, z, and 4 take 3i. Okay, so when we look at this problem, we're going to take the same approach. We've got 2 outside of z squared, take 3 take I in the z. We have our 4 take 3i left outside. So when we add in the third term, we've got z squared take 3 take I z plus -3 take I on 2 all squared plus 4 take 3i. And because we've added this in, we have to subtract it. And it's also multiplied by 2. Subtract 2 times the added term. So we've got 2 lots of 3 take I squared on 2 squared, which is 4. And that cancels down to 1 and 2. So now we've got 2 lots of z take 3 take I on 2 all squared plus 4 take 3i, and now we can simplify here and say that's subtract 9 take 6i plus I squared, which is -1, all on 2. And so now we've got 4z take 3 take I on 2 all squared plus 4 take 3i take 8 take 6i on 2, which is take away 4 take 3i. And so that cancels down, and we're just left with a nice 2 z take 3 take I on 2 all squared. Pretty complex, and it takes a lot of skill to be able to do that. So these completing the square factorized type questions over C are complex. We'll take one step further and now we'll look at solving these saved problems. When we look at solving these, there's two approaches. So if the question is simply solve, you can go through completing the square. And so if I was to solve one of these completing the square problems, and it was equal to 0, as it suggests. So with this part A, so I'm just going to put this in red because this is following on from the last question. We had that z squared plus z plus 3, and now it's equal to 0. So when it was factorized, and we had z plus 1/2 plus root 11 on 2i, so z plus 1/2 plus root 11 on 2i, and z plus 1/2 take root 11 on 2i as our factorization. If we apply null factor theorem here, so if we go apply null factor theorem, then we get z plus 1/2 plus root 11 on 2i is equal to 0, or z plus 1/2 take root 11 on 2i is equal to 0. When we isolate z in each of these scenarios, we get z is equal to negative 1/2 subtract root 11 on 2, or z is equal to negative 1/2 plus root 11 on 2, and of course don't forget the i's again. Now I'm going to take an alternative approach. So if you have this skill and you're good at completing the square with these complex numbers, then you'll just go down this path, complete the square, and use null factor theorem to isolate the unknown. If not, you're going to take an approach using quadratic rule. So we can see if we look at the discriminant in this scenario, b squared negative 4ac, we get 1 squared take away 4 times 1 times 3. So 1 subtract 12, which is negative 11. So when we go to solve, and we say z is equal to negative b plus or minus the square root of the discriminant on 2a, we get negative 1 plus or minus the square root of negative 11 all on 2 times 1, which is 2. So negative 1 plus or minus the square root of 11i on 2. And we can see that we get our two solutions. We get negative 1 plus root 11i on 2, or z is equal to negative 1 take root 11i on 2. So we get the exact same answer. We can split those up to make them both on 2, but I think you'll find that approach much simpler. Even when we look at b, which was much more complex, it's the exact same approach. So let's say 2z squared take z take 1 plus 1 is equal to 0. Then our discriminant is b squared negative 4ac, so negative 1 squared, negative 4 times 2 times 1. And so we've got 1 subtract 8, which is negative 7. And therefore z is equal to negative b, which is 1, plus or minus the square root of the discriminant, which is negative 7, all on 2a, which is 4. So that's z is equal to 1 plus or minus root 7i on 4. We get our two solutions. Z is equal to 1 plus root 7i on 4, or z is equal to 1 subtract root 7i on 4. Okay, so if we use that solving by completing the square and null factor theorem, then we will get the exact same outcome. Now I'm not going to look at all of these. We're going to look at D as our last one using the same approach. So we have 2z squared take 2, 3 take I, z plus 4 take 3I is equal to 0. So this one is a lot more complex, but it's still easier than completing the square. So A is 2, B is negative 2, 3 take I, and C is equal to 4 take 3I. So when we look at the discriminant, which is B squared negative 4AC, we get negative 2, 3 take I, all squared, minus 4 times 2 times 4 take 3I. So we get 4 multiplied by 3 take I squared, subtract 8 multiplied by 4 take 3I. And so this is 4, and we have 9, subtract 6I, plus I squared, which is take 1, subtract 8 lots of 4 take 3I. So this is 4 by 8, because 9 subtract 1 is 8. 4 times negative 6 is take 24I. We have 4 by 8, which is 32, or negative 32, and negative 8 by negative 3I is positive 24I. Now this ends up being 0, so we get a discriminant of 0, which makes our life a lot easier, because now we say that z is equal to negative b plus or minus the square root of 0 on 2 times a, which is 4. So we get z is equal to negative b, which is 2, 3 take I, all on 4. And there it is. There's our final simple answer, because that comes down to factor of 2 on top and bottom, 3 take I on 2. So there's alternate approaches here. When you're solving, you can make your own choice. If the question is factorizing, then you'll need to use that sum of squares or completing the square approach. Right. One last thing before we finish this lesson is I want to draw your attention to something called conjugate root theorem. Now, what conjugate root theorem says is that if a complex root exists, then the complex conjugate root must also exist. That is, if z is equal to a plus bi is a solution, then the conjugate a take bi is also a solution. Okay, and if we can draw attention to it up here, when we look at each of these complex solutions, you can see that the only difference is the conjugate. So we have a positive root 11i, now a negative, a positive imaginary component, and a negative. This one is a repeated term, so it actually has the same one twice. So if that discriminant is 0, it doesn't apply. Okay, so hopefully that lesson makes sense. We'll be able to move into higher order polynomials in the next lesson.